Hello and welcome back. This is the episode number 8 from the second block of theory lessons. In this episode, we will see past and current ocean color sensors. As you can see in this table here, along the years, there have been many missions, many sensors that have been launched. Of course, we are not going to see them all, we are only going to see some of them. Ocean color remote sensing from space started in 1978 when NASA launched the Coastal Zone Color Scanner that operated until 1986. We can see here an example of a chlorophyll image along the Canary Island, along the Northwest African upwelling region, retrieved by this Coastal Zone Color Scanner. The mission of this sensor was to measure water-leaving radiance at a limited number of wavebands in the visible domain and using that signal to deduce concentrations of phytoplankton pigments in the near surface layers of the ocean. Despite of the name of this sensor, the applications were mainly restricted to open ocean waters because the presence of other substances in the more turbid coastal waters were either masking or modifying the signal from phytoplankton. So it was called Coastal Zone, but it was mostly used for open ocean waters. Subsequent missions from different space agencies include other instruments like, for example, SEAWIFS, MODIS, MERIS, AVHRR, VIRS, OLCI. Okay, so let's go through them. And let's start with SEAWIFS. SEAWIFS is a NASA second generation sensor. The Coastal Zone Color Scanner was a first generation sensor. Okay, this is SEAWIFS is a second generation ocean sensor that was working between 1997 to 2010, and it was designed specifically to collect data for ocean biogeochemistry, ocean biological data. For example, it was designed to retrieve chlorophyll concentration. The advantages of SEAWIFS with respect to previous sensors encompassed 4 additional spectral bands that included a band at the 490 nanometer sensitive to chlorophyll variation. It was collecting data on a daily basis, so it could be used for real-time detection of short-lived harmful algae blooms. And this way, it could be used to monitor algae blooms and in many regions worldwide, like in New Zealand, in the Pearl River estuary, in the South China Sea, so in many, many regions. It was even used to detect and monitor Karenia brevis blooms along the Florida coast in 1999. But of course, it's also included some disadvantages. Some of the disadvantages of this sensor including, first, that it didn't have a band in the 683 nanometer region, which is the fluorescence peak of chlorophyll. Second, the optical properties detected were largely affected by an inappropriate atmospheric correction, and also they were affected by the absorption of sunlight by the color dissolved organic matter or by the scattering due to the total suspended sediments, and also it was affected by reflection of sunlight in shallow bottoms. Also, it had a coarse spatial resolution, which limited the study area to regions that they were very large, to regions that they were more than 1,000 square kilometers. This is an example of a SEAWIFS image, again for the Northwest African upwelling around the Canary Island region. And we can see here chlorophyll concentration. We can see the upwelling that is active. Okay. Another sensor is MODIS. MODIS is a third generation of ocean color sensors that was launched on board of 2 NASA polar orbiting satellites, the satellite Terra, that was launched in 1999, and the satellite Aqua, that was launched in 2002. This sensor, MODIS, provides daily images at 36 bands with 3 spatial resolution, 250 meters, 500 meters, or 1,000 meters, depending on the band. Okay? And about half of these bands are also used to retrieve sea surface temperature or also for doing atmospheric analysis. Another good thing about MODIS is that it includes 8 bands in the 405 to 877 nanometer spectral region, which are specifically designed to study ocean color, like phytoplankton concentration, biogeochemistry, Okay, so the advantages of MODIS with respect to MODIS, with respect to SEAWIFs, includes a fluorescence band at the 676 nanometer spatial resolution waveband that can be used to detect HABs. For example, there is a study in 2009 where they were able to identify 71% of the Karenia brevis blooms in the Gulf of Mexico, so that's very good. It also provides sea surface temperature data at the same time as the chlorophyll data, and this, of course, highly improves the accuracy of HAB detection. If you remember, some HABs prefer warmer water, like, for example, cyanobacteria. So if we can have sea surface temperature water images at the same time as chlorophyll images, we have a better indicator of the possible presence of a HAB. Okay. It also allows the estimation of primary production for algae blooms because it provides all the necessary parameters. Like, as we said, sea surface temperature, chlorophyll concentration, but it also provides photosynthetically active radiation and the daily diffusion attenuation coefficient. Also, it has a better spatial resolution than SEAWIFs that can guarantee the accurate resolution of HABs within areas that are still bigger than 1,000 kilometers square. This is an example of a MODIS Aqua satellite image for the Gulf of Mexico, when we can see here large chlorophyll concentrations along the coast, mostly. The limitations of MODIS with respect to other sensors are, first, that the fluorescence region, this 676 nanometer waveband, is a bit further than the actual chlorophyll peak, which is at 683 nanometers. This especially happens when the chlorophyll concentration is high. Also, MODIS images suffer greatly from the sunglint problem due to the sensor's design. Let's remember that the sunglint is this reflection at the sea surface, that is, the sunlight is reflected at the sea surface and is directed into the direction of the sensor, and the sensor gets blinded by this light. Okay? So MODIS, unfortunately, suffers from sunglint. We have some examples here. This whitish thing is actually sunglint. Also here, this is Crete. This is one of the Greek islands. And the problem is that where we have sunglint, we can't recover that data. There are some algorithms that allow for improving data recovery with sunglint problems, but we still might find some problems. Okay, this is another example. This is very, very clearly this band here. All this is sunglint. Okay, and the rest are clouds. So let's move to MERIS. MERIS was a third-generation sensor that was launched in 2002 on board the ENVISAT-1 satellite by the European Space Agency. One problem was that the ENVISAT mission ended suddenly in April 2015 when the European Space Agency suddenly lost contact with the satellite, and they don't know what happened. So the satellite just disappeared, just vanished. This sensor measured the solar radiation reflected off the Earth in 15 separate bands within the visible and the near infrared light from 350 to 1040 nanometers, okay, at 300 meter spatial resolution. So it had a very good spatial resolution. One application of MERIS was to detect blooms of cyanobacteria, and more specifically, there were some algorithms that they were developed specifically for cyanobacteria. One of them is the Cyanobacteria Index, or CI Index, that was developed for the Lake Erie in the US. Do you remember Lake Erie and the cyanobacteria problems? Well, there is one equation, one algorithm that was developed to use MERIS images to detect these cyanobacteria blooms, specifically for Microcystis aeruginosa, which, if you remember, is a cyanobacteria that they can produce microcystin, which is a very, very toxic toxin. Okay. The C-cyano index is a corrected version of the cyanobacteria index, and it was developed to avoid areas marked as dominated by cyanobacteria, when in reality we had a mixture of phytoplankton species and maybe even without cyanobacteria. So it was just a way of correcting the equation to avoid this problem. The advantages of using Meris instead of MODIS were that the fluorescence bands were closer, as we said, to the actual chlorophyll peak, so it was more suitable for detecting hubs than MODIS. The features of this sensor also improved the accuracy of the radiometric correction, so the information that was provided for hubs was more reliable than the information obtained with MODIS, and it also had two spectral bands that they were used to identify cyanobacteria blooms, while MODIS didn't include or doesn't include those bands. More advantages include the design of the spectral bands are also more suitable to identify other hub species, not only cyanobacteria, while MODIS cannot identify species. Okay. Also, the spatial resolution of Meris was higher than the spatial resolution of SIWIS and MODIS, and this allowed for a more accurate detection of hubs in smaller areas, like, for example, lakes or rivers. Okay. The disadvantage, because of course nothing comes for free, the disadvantage of Meris is that it was a commercial satellite and they did not provide the data for free to researchers. So researchers had to pay for the data. Satellite data are very expensive, and if you don't have an active project, you can't buy the images. This is just an example of a Meris chlorophyll A image in the Gulf of Lyon in France. Okay, and we can see here an algae bloom. So let's move to another sensor. Let's go to the AVHRR, the Advanced Very High Resolution Radiometer. This is a NOAA instrument that was designed for global studies at high temporal resolution. In fact, it passes the Earth twice per day, and it also has a moderate spatial resolution, approximately 1.1 kilometer. As you can see in this table here, this sensor has been launched on board of many NOAA satellites along the years, since 1978 until recently. Okay. The objective of this sensor, this instrument, is to provide radiance data for investigating clouds, land water boundaries, snow extent, ice extent, sea surface temperature, vegetation. So, as I said, it was it had multiple applications. Okay. This sensor includes two visible bands that are sensitive to phytoplankton scattering in turbid coastal waters. That means that this feature and the high spatial temporal resolution, it makes this sensor very useful for studying hubs. And also because it provides sea surface temperature at the same time. Let's remember, sea surface temperatures can help us to identify hubs. Because, for example, cyanobacteria, we know that they prefer warmer waters. So it is actually a good advantage that we have sea surface temperature images at the same time as chlorophyll. However, in comparison with MODIS and with Meris, it has less spectral channels. It has a lower spatial resolution, so it can only be used to detect large-scale hubs that occupy very big areas, okay, and cannot discriminate specific phytoplankton species, like Meris, for example. This is just a black and white image for you to see a bloom event, okay, that was taken in 1995. This is just for you to see that this sensor has been used for many, many years. Okay, this is another example. This is actually sea surface temperature retrieved from this sensor, and we can see a plume of warm water, okay, that was an indicator of an algae bloom. Okay. So let's move to the VIRS. This is a multidisciplinary instrument that was launched in 2011 on the Joint Polar Satellite System series of spacecraft. This is a multi-platform satellite, a multi-agency program that was jointly done by NASA and NOAA. Okay. It has 22 spectral bands that range from 412 nanometers to 12,000 nanometers, so from the visible to the near infrared bands. Okay. It has 16 moderate resolution bands with a spatial resolution of 750 meters, 5 image resolution bands with a spatial resolution of 375 meters, and 1 day-night band. This is, if you remember, this is the satellite that I showed you before, that it also works during the night, not only during the day. The advantages of this sensor is that the spectral coverage will allow for data products that are similar to those from SeaWiFS, but it also provides sea surface temperature, which is a product that we find, for example, in MODIS. The 750 meter spatial resolution across the entire scan provides twice the spatial coverage of MODIS or SeaWiFS. So again, it is an advantage, and it makes this sensor more suitable for coastal and estuarine studies in particular. Also, specific applications of this sensor include the operational forecast of harmful algae blooms, which is what we are actually looking for. And this is an example of a VIRS image of an algae bloom in the Gulf of Alaska. We can see here the phytoplankton, these swirls made of phytoplankton. Let's move to OLCI. OLCI, Ocean and Land Color Imager, is a sensor on board the Sentinel-3 satellite from the European Space Agency that was launched in February 2016. The objective of this sensor is to provide data continuity for MERIS, but for free. That's a good thing. This instrument allows biochemical measurements like concentrations of chlorophyll A or suspended sediments. It also includes several improvements with respect to MERIS. Of course, it's a newer sensor, and some problems with MERIS have been improved. For example, instead of 15 spectral bands, it has 21. And it also includes a channel at the 673 nanometer waveband, so it improves the measurements of chlorophyll fluorescence. Also, the spectral bands are optimized to measure ocean color over both open ocean and coastal waters. It also includes a mitigation system of sunglint contamination, so we will lose less data due to sunglint. It provides a complete coverage over land and ocean at a full spatial resolution of 300 meters, so it's quite a good spatial resolution. And it also has an improved temporal coverage of the global ocean. It actually has a revisit time of less than 4 days, while, for example, if you remember, in MERIS, the revisit time was 15 days. So that didn't make it suitable for short-lived harmful algae blooms. Okay. Also, the atmospheric and the aerosol corrections in this sensor have been improved, which, if you remember, atmospheric correction is a big problem when we work with remote sensing data. Also, as with MERIS, this cyanobacteria index and the C-cyano indexes can be used to detect large blooms of cyanobacteria. Let's not forget that OLCI is an improvement of MERIS, so these two indexes can actually be used also with OLCI data. There is also another algorithm, another product called the Maximum Chlorophyll Index that was developed to detect high-density patches of chlorophyll that can be used with both OLCI images and MERIS images. One limitation of OLCI for HAB detection is that it will flag high chlorophyll regions no matter whether they correspond to cyanobacteria blooms or to any other functional group, like diatoms, dinoflagellates, so it cannot distinguish functional groups. This is a limitation. Another limitation is that it can also report the presence of algae in coastal waters that have a large concentration of suspended sediments. This is because the optical properties in some wavebands are similar, so we might think that we are measuring chlorophyll, and in reality what we have is a very large concentration of suspended sediments. But okay, scientists are working on improving retrieval from this data, these kind of problems. This is just an example to show you an OLCI image. This is actually a harmful algae bloom, okay, that was captured by this Sentinel-3 satellite. Finally, we have the multispectral instrument, or MSI. MSI is an optical sensor that is on board of the satellites Sentinel-2 from the European Space Agency. Sentinel-2A and 2B are two identical satellites that they were launched in 2015 and 2017, respectively. They occupy exactly the same orbit, but separated 180 degrees. So each one of them is on one side of the Earth, and they are orbiting the Earth, separated by these 180 degrees. That means that the revisit time is twice if we combine both satellites. And actually, we have a revisit time of approximately 2 to 3 days at mid-latitudes, so this is very good for short-lived hubs. Okay. This sensor on board these Sentinel-2 satellites is designed to measure the Earth's reflected radiance in 13 spectral bands from the visible near-infrared to the short-wave infrared. So it goes a bit beyond other sensors. Okay. It also provides a better spatial resolution than OLTI on board Sentinel-3. If you remember, Sentinel-3 provides spatial resolution of 300 meters, while with Sentinel-2, depending on the spectral band, we will have spatial resolution ranging from 10 to 60 meters. Okay, so it's much better. And actually, if we compare the images taken from Sentinel-2 or Sentinel-3 satellites, we can see that with a 10 meters spatial resolution, the coastal features are much better than if we use Sentinel-3 with a 300 meter spatial resolution. This sensor, MSI, it also includes a shutter mechanism that prevents the instrument from direct illumination from the sun, so it avoids this sun glint contamination. Okay? And with this sensor, level 2 and level 1A and 1B data are not disseminated to users. We could retrieve level 2 data, for example, from the Copernicus Open Access Hub or from the Sentinel-2 toolbox that was developed by the European Space Agency through the Copernicus program. Okay, this is just an example for you to see an algae bloom that was detected by this MSI sensor on board Sentinel-2, and we can actually see this discoloration of the water due to the algae bloom. So, if you want to know about the remote sensing techniques, specific techniques to monitor hubs, please join me in the next episode.